Well, we'll go ahead and kick off the last seminar of the semester, and it's mighty quiet around OSU with all the students leaving town last week. But we've got a great speaker today. We have Dr. Daniel Livsey. He's a brand new research hydrologist here at the USDA-ARS lab in Stillwater. And he specializes in hydrogeology with interest in cohesive sediment transport, hydrodynamics, and stratigraphy. Most recently, before he was here at OSU, he was conducting research on cohesive sediment transport and hydrodynamics in rivers draining to the Great Barrier Reef. So he was in Australia. Pretty cool gig there, but prior to being in Australia, he worked for the USGS as a hydrologist. He worked for NOAA as a postdoc fellow, and he got his doctorate at University of California, but he does have Oklahoma ties. He got his undergrad degree here at Oklahoma State. So without further ado, I'll turn it over to Daniel to talk about lake level forecasts for use by managers and agriculturalists.
Sorry, yeah, that's hard word.
Thank you guys for coming, and I see some people online. Thank you for coming online. This work is an extension of what I was doing in Australia. We were doing a lot of flow monitoring estuaries in Australia, and we had sensors in the water, and sometimes crocodiles would literally bite our sensors and we would have no data. And so we need continuous flow data. And so we started predicting flow in estuaries based upon upstream water levels. So stream gauges that were upstream, much more reliable without crocodiles, and we could predict downstream water levels. And the predictions were getting so good that we realized that actually we maybe don't need to maintain these estuarine sites anymore. We can go back and periodically quantify the flow and make sure our models are predicting right. And so that was what we were doing there. And so when I applied for this job, I saw that there's all these lakes that our agency is responsible for. And I'm within the USDA, and there's this USDA watersheds program. Look at my little laser pointer. And within the watershed program, there's this NRCS small watershed program. It's the Natural Resource Conservation Service. And they assist partners to install small earthen dams across the United States. And since 1948, there's been 12,000 dams constructed. And within Oklahoma, there's 2,000 of these watershed dams, 2,107 watershed dams. There's a lot of them, and they're very small. Typically, if I get my numbers right, I think it has each, on the median, one lake has a drainage area of about 7 square miles. So they're very small reservoirs. 96% of the lakes have a drainage area less than 10 square miles. So they're very, very tiny. And but they're built in many places, and they can affect livestock if they flood. They can affect now, because with urbanization, you can actually flood cities, because some of these are now upstream of cities, like here in Stillwater, Oklahoma. But this is just a picture of a typical lake from this report, and you can see the grass. There's an earthen dam, and the earthen dams, they're usually about 50 feet high on average. And then you have the structure. It's called the embankment. It's made of earth. There's a principal spillway, which is just basically a pipe in the lake that will start to flow at a low level. And then you have an auxiliary spillway that allows water to flow over the dam before it actually overtops. And there was an application developed by the USDA called Dam Watch. And Dam Watch alerts project sponsors to potential overtopping of the lake. But Dam Watch, to my understanding, actually doesn't have the in situ water levels in it, because there's not enough monitoring data out there to actually know what the current level is. So what it does is it says, what is my nominal storage? And if I have so much rainfall in a day, then alert my manager, alert the people that you might get some overtopping, you might get a flood. And in this report, and this is back in 2013, they say, oh, well, these flood control dams have saved 85 million annually to Oklahoma's in this Oklahoma Conservation Commission report from 2013. So I imagine that number's higher today. But these dams are increasingly we're increasingly interested in these dams for two reasons. One, they're getting older, so many of them are beyond their project designed lifespan. And the other issue is urbanization. So there's a lot more people on the land. In many places, there's people downstream of these dams before it was just agricultural land. So, so when I came over, I thought, oh, it would be nice to do some water level predictions in these lakes. I basically just verbalized that text. So our motivation really is not to replace Dam Watch, but to augment it. And what we'd like to do is have low-cost pressure transducers installed in these small lakes. And so if you know the current water level from a pressure transducer, you pretty well can predict the next water level, next hour, next 24 hours. I'll show you, and that's the point of this talk. It just shows you that you can use pretty low-level algorithms and data to predict future water levels fairly accurately. Our approach is just to use something called decision trees. And what I did is I took data from the USGS. They monitor many reservoirs across the country hourly water level. And then NOAA, they observe a lot of meteorological data across the country. So these are two data sources that are very prevalent across the country and easy to download. And so I took just 3 lakes in Oklahoma based upon their drainage area. I just picked Lake Frederick. It's down in Tillman County. It's about the smallest drainage area that I could find. And that's still well above the most common drainage area, around 10 square miles, which I like, but that's about as small as I could get. So I'm calling that small. Lake Altus, its drainage area, that's out in western Oklahoma. It's got a square mile drainage of 2,800, and a big lake, Lake of the Cherokees, it's just 10,000 square miles. It's like off the charts. So I'm not even sure what the point is of doing this. I just thought I'd get a range to see how that goes. And then a decision tree is really simple, and I like it because I can explain it to farmers. So what we do is we ingest hourly lake level, and we compare that to hourly meteorological data. And we can discuss which variables we'll use in the next slide. But imagine you have a bunch of meteorological data, a bunch of lake level data, and you can say, well, how much has it rained in the past, and how much has lake level changed for all these years? And for these data sets, I think we're coming on like 20 years of lake level data, of hourly data that we can take in. So you can get there's plenty of data to train on. And a decision tree is pretty simple. If you have, let's just imagine you have 2 predictors, variable X, variable X2. The decision tree just says if X is below a certain value or greater than a certain value, then predict Y. And then it can incorporate multiple variables, X2, less than, greater than, predict that. You'll see these things, we call these nodes. And every time that there's a split to the tree, so we'll talk about the splits in the trees. There's another split. So this little tree would have 2 splits, and it would have these nodes. And in each node, right, at the terminus of each branch, you have what's called leaves, which is just the number of observations for that prediction. So there would be 4 observations here with y equals 2, 2 observations of y equal 1, and 1 observation of that. And this is called the minimum leaf size. So in your model, you have to specify how fine-tuned your model gets. So if you specify a model with a minimum leaf size of 1, you can fit the data perfectly, but it's probably not going to predict very well when it sees new data. And so you have to optimize your model for that. In the machine learning literature, they call it feature generation. Your feature is just your predictors. And so the approach that we did is to generate many features and then try to have an algorithm that determines which features are most important. So I drew a little cheesy map here with my lake here, a drainage area there, and some meteorological stations. And for this initial cut, I just went on the map and I said, oh, if there's a NOAA station within the drainage area, pick it. But if there's something north or west of it, also pick those. And I just picked the closest. And the reason is that storms generally come from the west in Oklahoma. And so hopefully that if you see rain here, it's going to get into the drainage area eventually. It's just going to have a little bit. And so that might give us some predictive time. And so for the predictors that we generated, for the different forecasts, I would just use the most recent water level and the rate of change in that water level. Different rainfall totals from hourly, from the 1 hour total, 3, 6, 12, the last day, the last week, and the last month total. For fun, I just put the mean surface air pressure in. That's just basically from my grandma. She used to have a barometer in her house and say whether rain was coming or not. So I said, oh, I'll just do that for fun. Actually, the algorithm never picked that up as important. So that was just me being silly. And again, you can do not totals, but average. It should be average there. Average, hourly, daily, weekly, monthly. And then none of our data really have soil moisture in it. And that's a problem, because what these models are basically doing is it's creating a pseudo rainfall runoff model, really. And the problem is that rainfall runoff relationship changes based upon ground cover and soil moisture. And I don't have that. And I want to be lazy. I just want to grab meteorological data only. I want to pretend to see how well the models could do in a kind of a dumb sense. And so what I did there, I just took the weekly and monthly average of air temperature, relative humidity, and dew point temperature. And the most important variable that came out of here was the monthly average, and that gives us a nice annual, it gives us the seasonality. So the model can actually have some seasonality within it. To figure out which features we should choose within all of those predictors for a given lake, we used something called a forward sequential feature selection algorithm. And so that sounds really fancy, but it's actually pretty simple. So in step 1, you have a list of predictors. Let's say A, B, C, D, and E. And you train your model for one variable, and you compute some statistic. In this case, we were using root mean squared error. And this statistic quantifies the error in the model, and it's skewed toward it. It is affected largely by larger errors because you square the error. So the root mean squared error. So the model says, okay, train each one with one variable and pick the one that has the least root mean squared error. Let's say that's variable C. In step 2, you train models C and A, CB, CD, and CE. So you train all possible 2 variable models. And the algorithm just marches along until you get to you could train all of the models, get all the way out to step 5. The number of steps just corresponds to the initial list that you have. In each step, you compute the root mean squared error of the model. And so this is just for one iteration of a lake. So for one predictor, which was just the antecedent water level, you can predict the next 24-hour, this is actually a 24-hour forecast. You can predict the next 24-hour forecast with just the past water level with about a root mean squared error of 0.2 meters. And then the model adds a variable, and oh, look, now we're down to 0.04. That's 4 centimeter root mean squared error, and down and down. And as you add number of variables, of course, this number usually goes down. Eventually, it'll actually go up because you start to include variables that are not causative, but they're just adding noise to your model. And then you can just select some threshold. So for me, I just picked 1 centimeter. So as soon as my variable that adds again, if it doesn't improve my model, if the root mean squared error doesn't improve by 1 centimeter, once it improves by 1 centimeter, stop the model. And then that's your final prediction. We talked a little bit. So once you have your features, you actually have to train your model. And any machine learning model, you want to optimize the parameters. And so for decision tree model, what I mean by parameters is, we talked about this earlier on, the minimum number of leaves in each node, or in each terminus, I should say. So that's n equals 4, n equals 2, n equals 1. So, and then also the maximum number of splits. So that's a split, that's a split. And the maximum number of splits is just the number of observations you have minus 1 is the maximum. But you don't need to go that far. You can actually have less. So this is sometimes called the depth of the decision tree. And this is the number of nodes. And then you can get a little more sophisticated and you can train mini trees. And this is called a bagged decision tree approach. And in this one, the number of trees, each tree randomly selects a portion of the data that you have available, runs through the process, and then you get mini trees. So you could have 1,000 trees, 1,000 learners that are learning, and then the final decision is just the average of the output. Okay, so this is a little graph of a model optimization for a tree, some decision trees where we're optimizing the number of splits and the minimum leaf size. So for this, I chose like 32 learners, so 32 trees. And you can see as the maximum number of splits increases, your objective function, this is a multi-parameter objective. And so it's hard to say actually what the units are. Actually, I tried to figure that out, but it's an aggregate of many different statistical parameters. And so as you increase the number of splits, of course, the model can predict better. And then actually the minimum leaf size, there was a slight effect there. So it's a surface. Anyway, and so the computer will run and it'll say, your optimum is, let's say, right there. You don't need to overfit the model. You don't want to underfit it. And so it has some criteria in which it picks. So that's what we did. So results, the general results here, I'm going to show a slide with forecast horizon. So this is how many hours ahead we can forecast. And so this would be the next hour water level in the lake. And this is the next day, 24 hours. And then I plotted the root mean squared error for these different data sets. In the machine learning approach, you basically have 2 steps. In step 1, you develop your model parameters. So basically the tree is developed. And that is an iterative process in which the model ingests training data, tunes the decisions, and then predicts on data that hasn't seen within that data set, what's called validation. And so you get a root mean squared error for your training step and your validation step. So that's an internal loop here. And then testing is when you take some data that was completely outside of this loop, and you predict some new data, and you try to test that on it to test whether the model is overfit or not. Machine learning models are really useful, but they're very prone to overfitting. They're so complex that you basically can fit random noise to anything, more or less, if you just let it go forever. And so you really need to test it on data that it hasn't seen before. And so to do that, I took the first 2/3 of the data that I had in time and gave that to training and validation. And the last third of the data, which is like 6 years, and I tested whether it would produce reasonable results or not. And this is expected for forecast studies. Basically, your error goes up the further you have to predict out. And so initially, I mean, if you want to know the next hour level, you can know it within a centimeter, pretty darn accurate. It's going to be, even with the next, so the next hour is like, you're going to know what that water level is. That's not too hard because lake level doesn't change that much every hour. And then by up to times 24 hours, your root mean squared error on your testing data set goes up to, 11 centimeters. So plus or minus 11 would be your confidence on that. Now, the issue with root mean squared error, it actually isn't, it can hide basically what your large, upper estimate of error is. It's the average of your error. It's not your most extreme uncertainty, on the prediction. And so here I give you a sense for that. Is on the left, we have, again, root mean squared error as a function of forecast horizon. This is for our smallest lake with forecasts observed water level at 8-hour interval, 8 hours ahead and 24 hours ahead. And you can see that the 8-hour prediction is better than the 24-hour, the blue circles, and the 24-hour gets it wrong sometimes. And this is the testing data set, I should say. This is data that the model hasn't seen. If you looked at the training data set, this would be almost a perfect line because the model can fit fire out of it. But that's the problem. So you really want to look at, always to really understand the uncertainty on your model and its performance, you always want to look at data that hasn't seen for that prediction. And this is the distribution of residuals from each prediction. And you can see that 8-hour forecast has a smaller residual distribution than the 24-hour one. The most extreme, residual is like right there. So you don't want to tell a farmer, my uncertainty on my model is 10 centimeters. It's actually something greater. You could be off by that much, which I don't even know what that is, but it's some greater value. And so that's a next step. We'll start to utilize these residuals to predict uncertainty on our models. But yeah, so just be careful of interpreting the root mean squared error. And now I'll just show you the time series results for the small reservoir and the medium reservoir. So our small one is Lake Frederick. It has a drainage area about 60 square miles. Our data is from 2010 to 2024. This is water level. And all the plots are meters from the auxiliary spillway pipe. So 0 means you're right at the auxiliary spillway. This vertical black line divides the 2/3 of the training data. This is training and validation, and this is testing. And in the left panel, you have 8-hour forecast, 24-hour forecast, and you can see it's doing pretty well. Yeah, so the training data set, you'd expect it to do well. If it's not, then you got a problem. You know, you're probably including some variables you shouldn't, or you're under training your model. But then the testing is where it shows whether it's working or not. There was some missing data in the predictors the model shows here, so you don't see any red. So the red is the forecast predictions, the black is the observations. And well, anyway, so at the large aggregate level, it looks pretty good. I'll zoom in next to a time period that was training, and this is for the largest. We'll zoom into this period, this largest rise, and we're actually when the water level exceeded the principal spillway here. And so you can see the 8-hour forecast would, I should make this, it's hard to see, but there's a red line going up, 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 up. And so at that point, you could actually give the farmer an 8-hour advance warning that water level is going to exceed your spillway. And that's really nice. And then you can ask, well, how well did my 24-hour one do? The 24-hour actually predicted when it was going to overflow, but it has this weird drop in water level right there. So that might be some overfitting in the model that we need to deal with, but overall, I'm really pleased with that. I'm not pleased with this persistent dip at the top, but and then here's the testing data set. So these are data the model never saw, and then we predict with those parameters. An 8-hour forecast is doing very well. It predicts the hydrograph within an 8-hour window, and the 24-hour forecast does pretty good, but it misses the peak. It says my peak is somewhat lower than what it is. So that's half a meter there. So that might be like, I don't know, 1/10 of a meter, like 10 centimeters maybe. So that's doing pretty well. I should say, for predictors, actually, for this lake, the algorithm selected the last 12 hours of rainfall from the most nearby station westward, the monthly average humidity, and the last 3 observed water levels. So those are all same to me. I mean, I basically said, I'm gonna pretend like I'm a dummy and let the model choose predictors. And of course, you want to give it a reasonable set of predictors, but it's also nice not to get too choosy with it, because then it automates the approach more easily.
Can you say those 3 again?
It was the last 12 hours of water, last 12-hour total, the mean humidity,
That's 12 hours of rainfall.
last 12 hours of rainfall, the average humidity, and then the last 3 water levels. So the trajectory of water at T minus 25, 26, and 27 hours. And so, yeah, that's how it did. And it varies by lake. So I did it for 3 lakes. And so the set of predictors varies. And what's nice is as the forecast horizon gets longer, the first like 8 hours, it just uses the last 3 water levels, and you can predict. So that's called an autoregressive. The lake levels are highly autoregressive. So basically the last recent water levels is a very good predictor of the future water levels. And you can predict using very simple autoregressive models, the first 6 hours of water level beyond, but then those autoregressive models, their predictive power becomes less as time gets on. And so, but anyway, that's autoregressive things, but that's that. This is the medium reservoir with a drainage area of 2,800 square miles. And again, it's the same plots. Black is observed, red is predicted. A vertical line separates the training and testing data set. And you have an 8-hour and 24-hour forecast. In this forecast, just zoom in and look at this peak that it missed. The model is missing right there. And so the 8-hour forecast and the 24-hour forecast miss it. This is the testing data set. Right there's the boundary between the training and the testing. And it predicts pretty well the 8-hour. It says, you would get a warning, a principal spillway is going to flow in 8 hours. Or here you'd say principal spillway will flow in 24 hours. But then your predictions are going to dink around, and it gets the duration. So basically what's nice is in terms of operations, if you're looking at this in real time, you would seeing a red line exceeding the principal spillway elevation. And then you would see, oh, it's declining. And so you would get a very good sense of how long this reservoir is going to flow in real time, 24 hours in advance, which is nice. That's the goal. The goal isn't to get the peaks. I mean, it would be nice to get that. I mean, that's important for understanding the total force that's exhibited on the dam and your downstream flow and floods and all that. But yeah, so what do we miss that by? We missed that by almost a meter, 75 centimeters there. So limitations, I got my numbers wrong, so I shouldn't try to remember numbers. The median lake area for our small watershed reservoirs is 2 square miles. It's really, really tiny. It's less than 10. The maximum is 72, and 96% of the lakes have a drainage area less than 10 square miles. There you go. That's the right numbers. And again, the smallest lake that we predicted was 58 square miles. So that's sitting around the biggest lake that we would have in our small watershed project. And the reason why I didn't go lower is because we don't have water level data in these small lakes. So I would really like to install water level measurements in these small lakes and see how they operate. And just from talking to people and from hydrodynamics and hydrology, the small watershed lakes are going to respond very quickly. And so that will test the limits of this approach, is whether you can do it. But it seems to be working around 70 square miles, it seems to work. But really, to test the approach, you need to go lower. Lay, a co-author, has actually been using gridded precipitation data from NOAA. We could do that as well. I was just doing something I could pull easily off an API, off the internet. And you can include stream flow data where available. I mean, that would be really the most direct predictor. But for these small watersheds, you're not going to have stream flow, most likely. They're not, USGS isn't going to be out there measuring the 10 square mile drainage area. And so really, I think precipitation data or meteorological data is the way to go. Decision trees are simple, but they don't actually provide estimation of uncertainty through their predictions. These probabilistic-based machine learning models, such as a Gaussian process regression model, are very powerful, but they are slow to train. They take a tremendous amount of computational power and time to get predictions. So I was impatient, so I didn't want to use those. We use those in Australia and they work very well, but you need parallel processing and you need a lot of computing power to running those. And I actually not smart enough to understand all the statistics behind them. They use very high level statistics, which I have a hard time grasping. I can grasp a decision tree. So I like using decision trees. And at the end of the day, we would like to have predictions with uncertainty also to give to the farmer. And this is just some outputs that we had for predictions on Australia on sediment transport. The black line is predicted sediment concentration in an estuary, and the red line is predicted flow within the estuary. And you can slap 1 standard deviation and 2 standard deviation uncertainty on your predictions. It looks nice, and I think it does give a farmer a much better grasp of how much uncertainty your model has instead of just the root mean squared error. And that's it. So thank you.
Questions? So I've got a question about possible integration of the soil moisture data.
Yeah.
Because, here in Oklahoma, we have the Mesonet and a lot of soil moisture measurement across the state. And I think Tyson Auctioneers work with Mesonet to, integrate rainfall to giving like daily forecast for any point in the state of what the soil moisture is. So
Yeah.
other opportunity, or do you think that would help? Because your forecast was pretty good, at least 24 hours out, but you think that would make it where you can predict lake levels even further out?
Yeah, just because of time, I limited it to 24. I could let it go out longer, and I think soil moisture would improve it. I tried accessing, because I worked for USGS before, so I knew the USGS website and NOAA website really well, and so it's just a matter of convenience. I tried to get on Mesonet, and I wasn't able to figure out how to download data easily. It's probably my ignorance, but yeah, soil moisture would be great. And And Lay asked, why didn't you use forecast data? You certainly could. And, and then you could even put on, you can integrate forecast measurements into that. I think, yeah, no, it's a great idea. I think part of me was wondering, like, I think we should run out our forecast further. One problem I have with this approach is it's not really, I wonder if it's not very causal. It's just more of a pattern matching thing, because it just says, if I've received this much rain in this watershed, and I have these conditions, and the lake level's done that, then predict that. So it just predicts what's already happened in that sense. But what happens if we got a really high precipitation event that this thing hasn't seen? And so machine learning models are very good at predicting what's happened within their domain. But once you start to extrapolate outside of that, you can get nonlinearities that might present big problems. And yeah, so your model, you'd have to, within that, you probably need to alert yourself to, oh, my predictors are outside the range they have been in the past. Caution user, like this is new terrain. And the model can continue to update itself, but it's those events that you haven't seen before that might cause a real problem. And that's one reason why I like the Gaussian process regression models. It's more of a probabilistic fit to your data. And the uncertainty bounds, once you get outside of your predictor range that it already seen, the uncertainty blows up. And so it actually shows up visually very easily. Like, hey, you're outside of your predictor range and you're extrapolating. And extrapolations are worrisome. And so it blows up the uncertainty on that. And so that would be I think that would be a good improvement.
Yeah. So the first thing I wanted to ask you was, by the way, this is really great.
Thanks.
You made a little mention about it. You said you made transport. So as you were presenting, I was thinking about, as a water quality guy, how I can piggyback on these efforts in terms of predicting water quality, like purple algal blooms, for example. One of the things we've been thinking about is how we can track the transport of water quality in the watershed. So the fact that you're looking at from that kind of small scale, it seems to speak to that idea.
Yeah,
Do
you
think
could.
That's something that we could incorporate into this effort that you.
Yeah, there's a guy out at Scripps. His work is in predicting algal blooms off of the coast of San Diego. And he uses something called empirical dynamic modeling, EDM. And the algal blooms off the coast of California are notoriously difficult to predict. There's no algae, and all of a sudden there's this massive amount of algae. And his models are really well suited for predicting algae blooms, at least for that. Like, he's shown that work really good. His name is George Sugihara at Scripps, and he's produced an R package called REDM. And so if you're interested in algae blooms, stuff like that, his models are very good. But you could use, I like his model very well because it predicts very spiky data. It's very well suited for picking data. There's not much change, all of a sudden, boom, there's this big spike. And his model is very well suited for predicting that nature. Some models are more smooth. His can predict really abrupt things. But yeah, you could. For these data, the concentration, there was a paper in Nature Geoscience that showed that they could predict sediment transport in rivers using just the ratio of current velocity to depth. It's a Froude number, basically, within the stream. And with the Froude number, they said, oh, look, we can pick all this concentration data. And so that's all I did. I just picked up that variable and stuck it in, and it works pretty good for our model. And then what's also nice about some of these models, instead of if you go into Excel and you fit some X versus Y model, some parametric model, it's a global fit to the data, and the parameters don't change with time. And so a lot of these processes, especially water quality ones, are non-stationary. And so that's particularly true for sediment transport in this river. What will happen is this was actually a river discharge event. And so the river brought in some sediment and elevated the concentrations. But then after the flow event, you basically just get tidal resuspension of the sediment. And if you keep plotting these data out with time, the concentration drops lower and lower and lower and lower, even though you have the same fruit number. And that's because you've winnowed out the sediment. So that's that non-stationarity process. And so when you look at a model, that's what is his name? Sugihara's model are non-stationary. They can deal with that and also with changes in temporal delays between the variables. So yeah, no, you definitely could. And you want to look at something called non-stationarity for those kinds of things. Yeah.
Just out of curiosity, have you ever tried to look at past events like predicting back in the future?
Oh, predicting
Like,
back.
yeah.
Oh, I suppose you could. The one thing this model relies on is it relies on the most recent water level.
okay, oh, okay.
And as soon as you get rid of that, the predictions go to the terrible. They're just like, you know, it's interesting. You have, and I think what that's picking up on is the you know, the current lake level has to do a lot with what it was recently. And that's the autoregressive behavior of the system. And so yeah, to predict what it might be in the past without lake level, might be difficult. Yeah, I think. I remember I did it once and I was like, oh man, this is not working. And I didn't even make the plots. I just threw it away and said, okay, I always need lake level. And so.
So I'm assuming you're using the water balance to predict the lake level, right?
It's more empirical than that.
Okay.
It's just simply the most recent water level, say for a forecast, say the 24-hour forecast. What I'm doing is to generate that, I look back 24 hours in the past to pretend that's where I was to predict that future state.
Okay.
And then it says, okay, that's the situation. Here's the rainfall recently, here's the humidity recently, and all that. And then it just makes a guess as it predicts. So there's actually, it's completely a giant decision tree. It's very empirical. Yeah.
I was thinking about ET, that's why I asked that.
Oh yeah, so ET is interesting, and that's why because I don't know much about evaporation in lakes. I just Googled predict evaporation in lakes, right? And there's actually some equation that's been used for a long time, since like 1950. And it has some name, I don't know, I don't remember the name, but it had listed in it, it was like the monthly air temperature and the humidity were like two, if you wanted to predict what evaporation rate was. So that's one reason why I grabbed that. Also, I knew soil moisture was important, but I didn't want to put it in my model because I was lazy. And so that's what I did. But yeah, no, those ET models you can, and that's how, you know, this looks kind of fancy, but you don't need a really in-depth understanding of the system. You need some general understanding to put in what you should. But yeah, with a little bit of help, a lot of people can do this. And I think a farmer could understand it. You could say, I put that in because this helps me predict evaporation or whatever. I don't know if I should check for online.
There's
I don't even know what time it is.
12:37.
Okay, so I'm not over time. No. Okay, good.
So your model actually did really good with just a limited number of parameters that you're using. Because I was thinking, oh, do you need the lake volume or a bathymetric study? And
Yeah.
you're able to predict that well without really having any of those additional pieces of data.
Well, I think one reason is there is the USGS develops these curves between lake level and storage volume. Right. And I think that's one reason why the model always needs to know what my recent lake level was. Because there's as lake level rises, storage volume changes with respect to change in height. And so if the model always knows where it was recently, it can be empirically on that curve somewhere. So there is probably an aspect in which that nonlinearity is being picked up by the model. Even if it's for a bowl-shaped lake or a V-shaped lake, that shape is within the height data in a sense. Yeah.
How does a farmer make use of this information?
So what I would like to do is have sensors in, say, some important lakes. Maybe this farmer has 10,000 cows below this dam, and he needs to get those cows out from below the dam before it floods. And so the idea would be to give him 24-hour in advance notice, like, hey, our model is predicting that you're going to get flow over this dam in the next 24 hours. You should move your livestock. And that could be converted to people as well. You could say, this thing is likely to flow in the next 24 hours, 48 hours. And what I would like to do is have different further forecasts, more than just 24 hours. You could do 48 hours, 72 hours, and then have probabilities. Like you have a likely probability of exceedance within this time frame with this probability. And then someone could decide what they want to do with that. And then we wouldn't actually have to decide. They could decide what they want to do with their cows. But if it were people, then there's probably authorities would get involved with that. But that's why this dam watch, the dam watch is used across the country. But it's agnostic as to what the water level is. I think, to my understanding, what I've been told, I've been trying to find documentation for it. It's used heavily, but I cannot find a technical report that shows me how it works. And what I've been told what does is it utilizes, say, this nominal flood storage, say it's the median lake design level. And then if you have so much rain, it says, oh, you're going to have an overtopping event. But the next 24 hours, the next day, it resets back to the nominal level. It actually doesn't track changes in lake level with time. And that's a simplifying assumption that I'm sure works reasonably well, but I don't think we really need to do that anymore. The cost of lake level measurements are fairly low. You need to have infrastructure to ingest the data and process it. But with a little bit of lake level data, you can get, I think, very valuable forecasts. You can give people warnings within a day. Yeah.
Daniel,
I was just asking about flood insurance or.
Oh, I didn't think about that. Yeah.
Insurance using this model.
Yeah. I guess if you were using, like Lay's approach, he was using gridded precipitation data to do similar stuff like this. And if you could ingest gridded precipitation data from climate models and start to do that. One big issue with predicting lake levels, it has to do a lot with the shape of the reservoir. And that changes because of sediment storage. And sediment storage is constantly, you're basically getting more and more sediment storage and less flood storage. And so that's one reason why you'd want to always continuously train these models as long, as most up to date you can predict the next bit. But yeah, you would have to use, that's a good question. You would want to use gridded data to train it and then use gridded downsample climate models be one way to do it.
yeah, I'm curious about how you see this being applied generally. You said there's 2,000 lakes in Oklahoma.
Yeah.
You did it for 3, but those 3 had decades of data to learn from. Yet we could put in depth monitors. What did you say? Pressure transducers?
Pressure transducer, yeah.
But that's, let's say we could do that.
Yeah.
And that's a big barrier in itself. But assuming we could, then we start collecting data from now.
Yeah.
And it takes how long? It's going to take many years.
Many years, yeah.
For those to be able to have the data to represent that storage group. And then we need good rainfall data for every one of those watersheds. And there's only a certain number of meteorological stations.
Yeah, I think
so. I think it's really cool what you've done, but I'm just curious about your thoughts about how it could actually be applied generally.
Yeah, so I think the first step would be to answer the part 1 from a statistical approach. Would start to train the models on 1 year of data and then see how it performs on that testing data set after that. And then increase your length by 2 years, by 3 years, by 4 years, and you would see a improvement in model performance as you get more data, right?
Sure.
So you could quantify that. It just depends. Of course, it depends on the history of that year. If you have a very dry year and lake level hasn't changed much, it's not going to be very informative to your model. But if you have a nice big swing, that's really good. So, and you could randomly sample 1 year, sample 2 years, and then test. Then you do all this. So I could do that. That's a good question. My inclination would probably be on the order of about 7 years of data just from like an El Nino La Nina cycle. So something that's, it'd probably scale to some large scale climate force, right? From a dry wet cycle within Oklahoma, whatever that is. And they can be very short and they can be very long. And so I imagine, yeah, something like that, probably on the order of 3 to 7 years, is my guess. Regarding the meteorological data, we have the Mesonet, and you have the Mesonet, you have gridded data from NOAA that you can ingest. So I don't think meteorological data is lacking in a large sense, because there's a lot of different data products out there. And if you looked at a map of NOAA across the state, I mean, it's just like they have measurements on a lot of places. But how that scales to a small 10 square mile watershed, I don't know. My gut is that it would do okay, because rain tends to come from the west in large bands of westward or eastward moving rainfall events. So even if your gauge is not right there in that reservoir, the rain's going to come over that, in a likely, in a probable sense. But and the more stations you get, and the better the prediction, hopefully. But yeah, I would imagine that's the problem. It's you do need lake level data to make these predictions. And my brain's just thinking is now there's a lot of satellite altimetry estimates of lake level. You could use that, and it's not very accurate, but at least you have something. But these lakes are very small, so they might even be below the resolution of some of those satellite approaches to getting your training set. But yeah, it's like, of course, yeah, it would be put in the lake level transducers now, and I think within 5 years you'd have decent predictions, and then within 10 you'd be going, I think.
I think you could learn a general model. Like, let's say you could learn, I don't know how many, across the country, or across the Midwest, where the hydrology is pretty similar. Let's say we have 100 stations or 100 lakes where we have data. Could you make a model that takes the shape of the lake and takes the characteristics of the surrounding hydrology, almost like in hydrology we talk about like regionalization. Could we do something similar? And then you wouldn't need to learn. Not, I guess what I should say is every lake doesn't need its own model. Almost like a process-based model, like SWOT, right?
Yeah. No, you could look at that. You could. We were looking at that in terms of, in Australia, we had, I forgot how many rivers we were looking at. We surveyed in 7 rivers, and we were trying to predict the size of flocculated mud in suspension based on hydrodynamics from all these different rivers. And all these rivers crossed large climatic zones. I mean, from dry to tropics, right? Just big gradient. And we said, okay, in the model, in the decision tree, I will tell it what river it's in and give it all the other relevant parameters, the categorical variable. And then I said, okay, that's one model. And then, okay, now don't tell it, let it try to figure it out. And including the lake information didn't improve the model. And so we could say, oh, this process is generalized. This model can generalize across these 7 lakes. So you can statistically answer that question. I think you might find that you need a category variable of something about soil type, or even climatic zone. You might start to get into, you need some category variable that tells it about whereabouts is it, and then the models might be able to start to create a global model. It might need categorical variables that tell it, I'm in a sandy soil or I'm in a clay soil, just to get that rainfall runoff pattern. Because if my drainage area is, what is my drainage area? So you could start building that. I tend to think you'd need something like that. I'd be surprised if you could create a generalized model with just rainfall and lake, and then that. So yeah, but you're right. That's a good point. And you would need to start getting some of those regional predictors in it. So that could be a soil type classification, stuff like that would be ideas. And then and vegetation type is important. And so that's why so stuff that rainfall runoff models would think about. You'd want to create surrogates for that.
And maybe I missed this, so I just wanted to make sure I clarify. Can this model be also used for like streams?
Yeah, you could really easily do streams.
Okay.
Yeah, we were predicting, and one nice thing about this is that, okay, so you can do something called it's called the partial autocorrelation function of precipitation on rainfall. And it shows like it asks the question, where is the peak correlation in lagged rain to water level change? And that number in this lake was 11 hours. And the model picked 12 hours. So I was really happy about that. So I knew it should be something like that. But you can do that same with stream level. You
Because
can,
I'm currently monitoring a lot of streams.
Yeah.
And so, you and I will talk to see how best I can be able to.
Yeah,
allow something like this to help the farmers.
yeah, I can get you in contact too with a colleague I had in Australia,
Okay.
and he was doing rainfall
Mhm.
stream flow predictions.
Okay.
I was going straight to the source. I just said, oh, give me my upstream flow and predict the estuarine flow.
Okay.
But he said, sometimes I'm missing that. So he started bringing rainfall sites in and predicting stream flow with very good prediction accuracy. And once you start looking at it, you'll get drowned in papers. Like this isn't really novel in a sense. Like it's just like, and you gotta be careful because there'll be another paper on, we use this machine learning to do that, and do that, and do that, you know, it's like,
Oh, sure.
Yeah.
Thank you.
So what are next steps for you with relation to this research, and then maybe more generally, what are?
Yeah,
some
I
of the
hope-
Big research.
I hope to get a pressure transducer in a small lake. I know some families around town that have some of this lakes on their land. And so I'm going to buy a pressure transducer and say, can I put that in your pond? And just see the timescales at which it changes. So I'd like to do that. There's some internal funding that we can apply for to hopefully scale some of that effort. I'll be giving this presentation in the fall to a dam safety conference in Colorado. And yeah, I think most of it was just a proof of concept to say like, hey, this can be done, and you can put lots of bells and whistles on it if you want. And so I might be pretty much done with it. I mean, I might write a little paper and then say like, what I want to do is scale it and try to use this to motivate additional funding. I think the next step I might do is on some weekend, I'll let the computer roll with the Gaussian process models and just see how it does and see what outputs I get. And so that would be a step forward. But I really like the decision trees. It's something that's so they're very flexible and they're easily explained. And so, but the Gaussian process again has that nice estimation of extrapolation built into it. So.
On this one, what do you think those little?
Oh, these little under predictions, that's that persistent unprediction at the peak.
Okay.
And what's happening is this is a problem in the model. It uses the last 3 water levels. So at some point, the last 3 water levels start to decline. And then it says, predict down. And and so it doesn't know that it's at the peak of a hydrograph. And so that's a problem. I've thought about creating like, you need something to tell it like, I'm at the peak, don't behave like that, or something like that. But it's because it's a simple model, and it's just saying the rate of change is approaching 0, even going negative, drop negative. So that's what it's doing. I mean, it's a little bit ugly, but it's yeah, it would be nice to fix. That's that.
All right, any other questions? All right, let's call Chris.
That's all right.
Well, thank you all for coming and participating.
I stopped sharing, but you're still there.
Yes.
Okay.
So I hope everybody has a great summer. And if you have any follow-up questions or ideas, please let us know. But thanks again for joining us.